All right, hello everyone. Thanks for coming to Nick's thesis defense. I first met Nick in my aircraft dynamics course, and then I didn't see him until my algorithmic motion planning course. And towards the end, he approached me and he said he was thinking about doing research, maybe thesis research for his master's on motion planning. And he said, I want to solve the hardest problem in the world. I want to have autonomous systems reacting to everything outside. I'm like, okay, let's slow down. Let's read a little bit and let's start with fast motion planners. You want to do fast motion planners? He's like, no. I want reactivity at every level. But anyway, I was able to calm him down and said, that's not how research works. We are slow. So I think beginning of summer last year, he actually started his research. And by the end of summer, he already had a paper, RAL, and he took a pause and he worked on another idea and he's about to write another paper. So I let him take away from here.
Yep, so my name is Nicolas Perrault, and I'll be talking about my research on kinodynamic sampling-based motion planning algorithms with massive parallelism. So to motivate this research, here are some successful examples of autonomous systems that we see in our world today. On the left, we have an Amazon robot working in a warehouse where there's a lot of very repetitive motions and a constrained environment or a structured environment. On the bottom, we have these drones operating in the agriculture space where there's quite simple environments. There's no obstacles or moving obstacles. And again, we have this very structured environment. And the most interesting example would be these Waymo cars, which do have these dynamic environments, but even they rely on the structure of the roads and the patterns that we see there. And their behavior can also be quite conservative and kind of not making the most intelligent decisions along each step of the path. But what we're not seeing a lot of are very dynamic systems operating in very unstructured environments near their dynamical limits, like these drones flying through the woods. And this is a very difficult problem because the robot must sense their environment, estimate their state, and choose an appropriate reaction all in real time. And this part of the problem that I've been working on is choosing an appropriate action through motion planning. So how do we figure out how to get from point A to some goal region? So the challenge that I've been looking into is how can we design a motion planning algorithm that can quickly solve this motion planning problem for systems with complex dynamics. And if we look at the robotics stack, we see LiDARs operating at around 100 hertz. We have control loops operating from 100 hertz to far faster. But this motion planning problem for very complex dynamical systems can take seconds to tens of seconds to come up with solutions. So I've been looking into ways of how can we bring that motion planning problem closer towards what we're seeing with our sensors. So to formalize the motion planning problem a bit, I've been specifically looking at the kinodynamic motion planning problem, where we also consider the dynamics of our system. So our goal here is to find a control trajectory U that yields a feasible induced trajectory X that is propagated through this differential equation. And this trajectory needs to remain in this valid set of states. And the valid set of states not only considers workspace obstacles, but it also considers the constraints that we have on our dynamics. So limitations on things like acceleration, velocity, and turning angle. And we need it to end in some goal region of our state space. Now, the simpler version of this problem, known as the geometric motion planning problem, is already p-space complete, and this one does not consider the dynamics of our system. So it's quite a challenging problem. But when we're planning in the state space, which is a very high dimensional complex topologic space, and we have these kinodynamic constraints where we have limitations on things like acceleration, this problem becomes significantly more challenging. So a way of tackling these this kinodynamic motion planning problem is with sampling-based motion planning algorithms. And for the and I'll be calling these SBMPs. And a kinodynamic SBMP traditionally grows a trajectory tree through the state space until it reaches some goal region. And these kinodynamic SBMPs have these two common subroutines where we're doing node selection and node extension. And these are repeated thousands of times. So I'll walk through a kinodynamic SBMP at a high level. First, we have the node selection phase. So if we have some existing tree like this, we can randomly sample the state space with this orange node. Typically, we perform this nearest neighbor search where we are trying to find which node in the tree is closest to this orange node. We then generate some trajectory segment from that node and perform collision checking over it. And we add it to the tree if it's valid. In this case, it's invalid. And then we repeat that process again where we do node selection and extension, selection, extension, until eventually we reach this goal region. So if we look at existing work, there are plenty of kinodynamic SBMPs that exist that have been around since the mid-90s with RRT, and there's been a lot of iterations of these algorithms. But if we look at the planning time taken for this 12-dimensional system on this house environment, it takes these algorithms almost a minute to come up with a solution. So that's nowhere near the rate that our LiDARs are working at, and it's nowhere near that loop that we're looking for. So the question becomes, why are these algorithms still operating so slowly, even though they're well established and there's been plenty of iterations on them? And will they ever be fast enough? Will hardware ever be at the level where we can use RRT and plan at 100 hertz for this 12-dimensional system? And the answer to that question is kind of hinted in this plot here, where we're looking at the clock frequency of different processors throughout the year. So clock frequency is on the y-axis, and that clock frequency relates to how quickly is our core able to complete a very basic operation. And on this circle that I've drawn is when SBMPs were originated. So they were originated during this time of rapid clock frequency growth. So during this time, algorithms like RRT and these other kinodynamic SBMPs were getting faster and faster throughout the years because they rely very heavily on an increase in clock frequency. However, in around 2005, we see a flat line in clock frequency, and now the improvements are very small year by year. So we're no longer seeing these big improvements in the traditional kinodynamic SBMPs. Now we have had hardware improvements over the years. It's just been in a different way. And these green data points are the data we were just looking at, clock frequency. And right when clock frequency started to flatten out, we see an increase in the number of logical cores on processors. So instead of making a core have a higher clock frequency, we're adding more cores to our processor so that we're able to do tasks in parallel. So today, improvements in computers rely very heavily on an increase in parallelism through the addition of logical cores. An example of this would be we now have a multi-core CPU with 4 cores instead of a single core device. And instead of doing these tasks serially, if they're independent, we can do them in parallel, assigning 1 to each core, and we can do them in a quarter of the time. Now, if we take this to the extreme, instead of having a 4-core processor, we have many core processors, which are GPUs, that have tens of thousands of these very simple cores. And this plot here on the y-axis shows the throughput of these devices. So that's the number of operations per second that we're able to complete. And these GPUs have massive amounts of throughput, even compared to multi-core CPUs. And this throughput is increasing exponentially year after year. Now, this is pretty exciting, but since these GPUs have so much parallelism, they're a very specialized type of processing unit. So they're not as robust to different algorithms as a multi-core CPU is. You have to design your algorithm with their execution in mind. So we have to design our algorithm with these GPU fundamentals in mind. So the first one is we want to maximize thread independence. So when we execute some task on the GPU, we launch a set of threads, and we don't want a thread's progress to be dependent on the result of another thread. We want these threads to execute completely independently from one another. Another thing is we want even workloads across threads. We don't want one thread doing a massive amount of work while another thread is doing some very simple task, because this creates an uneven distribution throughout our device, which is also inefficient. And the last thing is we want to minimize thread divergence. So GPUs operate with this single instruction multiple data, where a single instruction is applied to multiple threads in parallel. And if we have an algorithm that has a lot of nested conditional statements, and our threads are diverging in their execution paths through these conditional statements, they'll be doing different instructions, or they're requiring different instructions, and this is not great for this single instruction multiple data. But this plot got me excited because of the massive amounts of throughput that these devices offer, and maybe we can combine these high throughput devices with multi-core CPUs and GPUs with the motion planning problem. So if we look at existing work for parallel motion planners, it falls into two categories. The first one is for multi-core CPU parallelization, and we see two types of parallelization here. One is called coarse grain parallelization, where we're actually growing multiple trees in parallel, one per core on the device. And the other type of parallelization is fine grain parallelization, where we're parallelizing the process of growing a single tree. And we see this with this VAMP algorithm, which is for manipulators. But both of these algorithms are strictly for the geometric motion planning problem that does not consider the dynamics of our system. And if we look at parallelization for GPUs, we have this GMT algorithm, which again is for the geometric motion planning problem. And this algorithm actually doesn't grow a tree. It relies on an existing set of samples and does a parallelized graph search over the set. But if we look at what exists for GPU parallelization for the kinodynamic SBMP, there turns out to not be any research focused on these. So that got me excited. And I wanted to look at why nobody had tried this. And it is actually quite a hard problem to parallelize, because these classic kinodynamic SBMPs rely on thousands of iterations of node selection and extension, which are hard to parallelize, because in order to select the best node, you need to know the most up-to-date information on the tree. So in order to have good growth through the state space, you need to serialize this process. So that's where my thesis comes in, where maybe instead of using these existing kinodynamic SBMPs, we can design a new SBMP specifically for these highly parallel devices that suits the GPU fundamentals, so they're efficient, and we still have good growth efficiency through the state space. So that brings me to my contributions, where my first contribution is an algorithm called KinoPax. And this is a first of its kind GPU accelerated kinodynamic SBMP that focuses on solving this kinodynamic motion planning problem as quickly as possible. And we're able to do this now in milliseconds. And we're able to achieve around 3 orders of magnitude performance increase over previous state-of-the-art methods. And my second contribution is an extension on KinoPax called KinoPax Star, which is an asymptotically near optimal variant of this algorithm. So in addition to just solving the motion planning problem quickly, we actually are asymptotically near optimal when planning over extended time durations. So first I'll talk about KinoPax, and then I'll go into KinoPax Star afterwards. So KinoPax stands for Kinodynamic Parallel Accelerated Expansion. And the key part of our algorithm is that we're decomposing this iterative tree growth process of node selection and node extension into these 3 massively parallel subroutines. So instead of performing tens of thousands of iterations of node selection and node extension, we're able to come up with solutions in tens of iterations. So I'll walk through each of these parallel subprocesses at a high level, and then I'll go into detail on each of them. So the first subprocess is node extension, where instead of extending from a single node, we're extending from a set of nodes many times in parallel. Our second subprocess is this decomposition update phase. And Kinopax uses a state space decomposition. So we discretize the state space and we use this discretization to keep track of our exploration progress throughout the state space. So during this subprocess, we're updating our metrics on how well we've explored the state space and which areas need to be further explored. Our last subprocess is this node selection phase, where instead of selecting a single node to extend from, we're selecting a set of promising nodes in parallel. And again, the key idea here is we are able to find solutions in tens of iterations instead of tens of thousands. So going into the first subprocess, we have node extension, where a traditional SBMP has some node that it would like to extend from. It generates a trajectory segment, it checks for collisions, and it adds it to the tree if it's valid. And one easy way of parallelizing this is to instead extend from that node lambda times using lambda threads. So that looks something like this, where each thread is responsible for a single trajectory segment. And if we look at our GPU fundamentals, this is actually quite good for parallelism because each thread generating its trajectory is independent from another thread generating its trajectory. And Kinopax takes this a step further by extending from a set of nodes in parallel. So we have this set of nodes, the extension set, and each of them are extended lambda times. So we're using VE times lambda threads, and each thread is responsible for a single trajectory segment. Now, the next question is, how do we determine which of these trajectories we want to keep? So obviously, we can discard the invalid ones, but it turns out that it's not great for us to actually keep all of our valid trajectories. And there's two main reasons for that. One, we have limited memory on GPUs. We have around 24 gigabytes on a desktop GPU. And another thing is we're going to have a lot of very unnecessary trajectories. We might have trajectories already in our tree that are very similar to those being generated, and these would just be a waste of space. So what we need is a way of identifying a promising trajectory and figuring out which of these are good. So what Kinopax does is we use this state decomposition R, which are these regions through the state space. And each of these regions has an associated acceptance probability with it, with a higher probability being associated with a more promising region. So how this works for determining if a trajectory is promising, if we were to zoom in on one of these regions, it has that acceptance probability that we see here. And if we have two trajectory segments coming off of a node, what we do is we decompose that region into k finer regions. And to determine if a trajectory is promising, we say, if the subregion is unoccupied, we determine that trajectory is promising. If it is occupied, we determine it promising with probability of the larger region, so 20%. So the result of that will look something like this, where this right trajectory was deemed promising and the left was not. And if we look at the result over many trajectory segments, it'll look like this, where now we have this set of orange nodes, which we call the unexplored set, or VU. And these orange nodes are the set of newly generated promising nodes. And an important thing that I'll recall later is that these orange nodes, the unexplored set, are not yet in the tree data structure. They're in a separate data structure. And that's for parallelism efficiency reasons. We'll add them later. But these dotted orange lines represent them not being in the tree yet. So if we refer back to our GPU fundamentals, we actually are quite efficient on a GPU. We have complete thread independence. So the trajectory generation is independent. A node acceptance determination is also independent. So one thread determining its node is promising is independent of another thread determining if its node is promising. We've also designed this data structure to store VU as a data structure that is able to be inserted in parallel. So threads are able to insert their nodes to this data structure completely independently. And we also have pretty even workloads. Since threads only generate a single trajectory segment. And additionally, a thread's computation to determine if its node should be accepted or not is constant for all nodes. So our next subprocess is this decomposition update phase, where we're trying to determine which of these regions are promising, and we're trying to determine how do we get these acceptance probabilities. So what Kinopax does is it actually collects data during this node extension process that is used to update these values. So for each region during the node extension process, we keep track of the number of expansions from a region, the number of collisions from a region, and the coverage of a region. And the coverage is how many of those subregions have we occupied. Then for our metrics, we use these well-tested state exploration metrics from existing motion planning algorithms like Cyclop, which provide a score value to each region. And a region has a higher score if it is less visited, so we have less nodes landing in it. It has a high free volume. That means a higher percentage of the region is in the valid set of states. And we have a low amount of coverage in the region, so a low number of those subregions are occupied. We then can turn that score of all visited regions into a probability through normalization. So what this process looks like is we launch a thread for each region that has a node in it. Each thread calculates the score of its region. We then perform this parallel reduction to get the sum of all scores. And then we turn that score into an updated acceptance probability. So these values have been updated based on the new data that we've generated from node extension. And if we refer back to our GPU fundamentals again, we're actually very efficient on GPUs for this subprocess because the score calculations are completely independent for each thread. And more importantly, we have no thread divergence in this subprocess. So each thread is following the exact sequence of instructions. So we actually spend very little % of the time in this subprocess. And another good thing about using this decomposition is that our decomposition is actually not a graph. We don't keep track of neighboring regions per region. So that makes it quite lightweight to implement. And additionally, since we can update them in parallel, update these acceptance probabilities, Kinopax can actually use a very fine decomposition compared to other serial SBMPs that use a decomposition. So this brings us to our node selection, where we're now trying to determine which nodes in our tree we would like to expand from. And how traditional SBMPs do this is they typically use this nearest neighbor search. However, this nearest neighbor search is actually not great for parallelism for a few reasons. One is that it's dependent on the current tree. So in order to select the best node, we need to know the most up-to-date information on the tree. Another reason is that it has varying computation time. So depending on where this sample is within our state space, the number of instructions will vary, which is not good for even workloads. And lastly, this computation has log n complexity. And for these kinodynamic motion planning problems that require many nodes, this computation can actually become quite expensive. So what Kinopax does instead is we probabilistically add nodes to this extension set VE. So how this process works is we launch a thread for each node in the tree. Each thread then looks at the associated region's acceptance probability, which has now been updated with the new extension information. And we randomly add nodes to the extension set with the probability of its region. So that looks something like this, where these two nodes were deemed promising and they will be extended in the next iteration of propagation. Now, if we look at our GPU fundamentals, again, we're pretty efficient here because each thread determining if a node should be added to the extension set is independent of another thread determining if its node should be added. Now we have this other set of nodes that I mentioned, this unexplored set that have not yet been added to the tree. So now in this part of the process, we need to add these to the tree. So what we do is we launch a thread for each node in the unexplored set. Each thread then adds its node to the tree and then adds its node to the extension set. So now we have this new set of nodes that we're going to extend from in the next iteration of parallel node extension. And the GPU fundamentals for that process are quite good as well. We have no thread divergence. So each thread is adding its node to the tree and then adding its node to the extension set. So we spend very little time doing this as well. So we then repeat that process of these three sub-processes until we find a solution trajectory. And again, the key point is we're able to find solutions in very few iterations of this. And here we find a solution in 21 iterations. Now, Kinopax is also probabilistically complete, meaning if a solution exists, the probability that we fail to find a solution as we run the algorithm for infinitely long approaches 0. Now, the intuition behind that is that each node in the tree is lower bounded by a probability epsilon, which is greater than 0, of being expanded. So every node in the tree is expanded infinitely often. And additionally, each trajectory generated is lower bounded by a probability epsilon of being accepted. So that means new trajectories are being added to the tree infinitely often. Therefore, we have probabilistic completeness. Now, if we look at our experiments, we tested this on 3 different environments of varying difficulty. We also tested it on 3 different dynamic models of varying difficulty. And we compared it against these 4 serial algorithms, and we performed coarse grain parallelization for fairness. So for each of these algorithms, we launched 24 instances of them and returned the first solution found. So we ran them on the CPU and returned however many cores we had and the time taken to find the first solution. For our GPUs, we ran it on 2 GPUs. One was a desktop GPU with 16,000 CUDA cores. And we also ran this on an embedded GPU, which is a low-cost GPU that can be fitted on a drone with 1,000 cores. And for all of our testing, we used the same method for state propagation and state validity checking. So if we look at the results for the 60 double integrator, you can't really see the result of Kinopax. You can see it for Kinopax on the embedded GPU, but I'll convert the y-axis to log scale. That looks like this. So on our desktop GPU, we're able to solve all of these problems in less than 6 milliseconds. So that represents an 85 times improvement on the first environment compared to all the reference serial solutions, a 287 times improvement on the second environment, and a 433 times improvement on the third. If we look at some more complex dynamics with this Dubin's airplane that has a harder or tighter turning radius, or it can't turn very tight, we solve all of these problems in less than 7.5 milliseconds. And now you really can't see the difference. You really can't see the data for Kinopax on either the embedded GPU or the desktop GPU. So I'll convert it to log scale. And that looks like this. And one interesting thing to look at is the difference in results of these serial solutions when comparing it from the double integrator to the Dubin's airplane. So this is the data for RRT on both of those systems. And the difference on the Dubin's airplane is quite significant. It significantly slows down RRT by around 22 times or 20 seconds worth. And we have similar results for these 2 serial solutions. And EST has the least slowdown, but it still slows down by 4 seconds. If we compare this to Kinopax, we have pretty similar results where Kinopax only slows down by an average of 2 milliseconds compared to these other serial solutions. And this provides evidence that as this problem is becoming more difficult and we're requiring more nodes and more trajectories, this better suits these highly parallel devices because Kinopax is able to generate many of these in parallel. So we're actually able to kind of mask the fact that this problem is much harder with the massive amounts of parallelism that it offers. Now, for the 12-dimensional nonlinear quadcopter system, we see a massive difference, and I'll convert it to log scale. Where Kinopax on the GPU or on the desktop GPU is 3 orders of magnitude faster than all reference serial solutions on environment 3. And we're 1,720 times faster than the best performing serial solution on environment 3, which is EST. And keep in mind that this is using coarse grain parallelization. So there is some kind of parallelization going on, and it provides evidence that instead of using existing algorithms and doing some kind of coarse grain parallelization, we need to be designing new algorithms that are much better suited for the improvements in hardware today. So we're able to solve all of these problems in less than 25 milliseconds on the desktop GPU and less than a second on the embedded GPU. So we can now look at the search characteristics of Kinopax, where again, we're able to find solutions in low number of iterations, here for 9 iterations. And this is 3 iterations of the 12D nonlinear quadcopter system. And we have this pretty efficient tree growth. So these pink nodes represent the newly added nodes to the tree in that iteration. And we're not wasting a lot of resources growing into spaces or places of the workspace that we've already visited. So it's expanding quite efficiently. We're also expanding pretty massively. In 3 iterations, we've covered a huge amount of the workspace. And another thing that we noticed is that the solutions produced by Kinopax are quite intuitive, where they don't wander through the states or through the workspace like we might see for a traditional serial SBMP. So we found that pretty interesting, but we weren't able to say anything formally about the quality of solutions that we were finding. So we wanted to extend Kinopax to an asymptotically near optimal planner so that we were able to provide some kind of guarantees on the solution quality found. So that brings us to our second problem, which is this near optimal kinodynamic planning problem. So in addition to just solving the motion planning problem quickly, we wanted to find near optimal solutions. So to formalize this problem, this asymptotic near optimal kinodynamic motion planning problem, it's very similar to the previous problem where we're looking for this solution trajectory X. However, now as our algorithm runs for n iterations and as n approaches infinity, we want the cost of our best solution to be within delta of the optimal solutions cost. And to do this, we make a few assumptions on our dynamical system. One, that it satisfies Child's condition, and that it's Lipschitz continuous. And we also assume that our cost function is Lipschitz continuous. So if we look at Kinopax and what are the issues with Kinopax that do not allow us to achieve this near optimal planning, well, there's a few issues. One, we have no cost metric throughout the planner, so we need to add that somewhere. And additionally, with the behavior of the algorithm, we actually struggle to improve upon solutions found. So in this plot, we ran 100 simulations of Kinopax, and we have cost on the y-axis and time on the x. And Kinopax quickly finds an initial solution, but as we plan for an extended duration, we don't see a reduction in the cost. It stays where it is. So that's an issue with this asymptotic, we don't achieve this asymptotic near optimality. So how can we change Kinopax and how can we change these subroutines such that we have this behavior that we're looking for? Firstly, we need to add a cost metric to our planner, and we're going to add that to our decomposition. So we're going to keep track of the cost to reach each of these regions. And additionally, we need to change the behavior of our node selection and our trajectory acceptance. So instead of just expanding through the state space and exploring or reaching unexplored regions, we actually want to improve how we have reached these explored regions. So that brings us to Kinopax star, which is an asymptotically near optimal variant of Kinopax, where again, we have these 3 subprocesses, and I'll walk through how they work at a high level and how they differ from Kinopax. So the first subprocess is very similar to Kinopax. We're extending from a set of nodes. However, now the acceptance criteria will change so that we have this asymptotic near optimality. And for our second subprocess, instead of doing a decomposition update, we have this node pruning process, but we're using data gathered during our node extension to tell us which nodes in our tree are no longer necessary to achieve these near optimal solutions. And our last subprocess is this tree update phase, where similar to Kinopacks, we are adding new nodes to the tree that were generated during node extension in parallel. So going into node extension, again, we are extending from a set of nodes, each of them lambda times. So we're launching VA times lambda threads. And now the set of nodes is called the active set of nodes. So our acceptance criteria has now changed though, where we only add a node to the unexplored set if it is the lowest cost that we've seen in that region. So how we do this is we actually keep track of the cost to reach each region, where if a node is not in that region, it has a cost of infinity. And how do we actually update these cost values for each region? Well, we do this with these atomic operations. And an atomic operation is a thread-safe procedure that guarantees an ordering constraint on memory accesses. So if we have two threads accessing the same region's cost value, like here, this guarantees that one thread changes the value and then another thread changes it, instead of both of them changing it simultaneously, which is a segmentation fault in parallel programming. Now, these atomic operations also have a nice property where the changes made by a thread are visible to other threads. So if a thread changes that value and another thread reads the value, it'll actually see the updated cost value. So this actually allows us to keep track of the lowest cost to each region during this node extension process. And it allows us to update these values as this node extension is progressing. Now, these atomic operations do have a performance trade-off where they are more computationally expensive, but we need to make this trade-off in order to have a much more informed node acceptance decision. So if we chose not to do these atomic operations and we had a scenario like this where many trajectories were all landing in the same region, we would not know which of these had the lowest cost, and we wouldn't be able to actually update the cost value of that region. We would have to do that in a separate process by serially scanning through each trajectory, which would be quite expensive. So this atomic operation allows it to do this pretty efficiently. So the result of the node extension will look something like this, where these three nodes were the lowest cost nodes in their region, and they are added to this unexplored set that again is not yet in the tree. Now, if we refer to our GPU fundamentals again, for thread independence, it's exactly the same as Kinopacks. For the even workloads, we've added these atomic operations, which are slightly more computationally expensive, but they actually don't affect thread independence. So a thread performing this atomic operation doesn't block another thread, which is pretty interesting. So our next subprocess is this node pruning phase, where we're trying to determine which of these nodes in our tree are promising. So similar to Kinopacks, we use the data generated from node extension, which is these updated cost values for each region, and we use that to guide our pruning. So a node is pruned from the active set VA if it is not the lowest cost in its region. And if it's not the lowest cost, we add it to the terminal set, which are these blue nodes, and these nodes will never be extended in the future. So how this process looks is we launch a thread for each node in the active set. We then check if each of these threads are the lowest cost in their region. In this example, it's no longer the lowest cost because we have this new node here. So that node is moved to the terminal set. So now we have these three nodes that will be extended in the next iteration of node extension. Now this form of pruning is actually the simplest that we have, and in our actual implementation, we provide a tuning parameter that varies the pruning process, but this is the simplest version. So our next subprocess is this tree update phase, where again, similar to Kinopacks, we are adding these nodes in the unexplored set to the tree in parallel. So similar to Kinopacks, we launch a thread for each of these nodes in the set. If they are the lowest cost in the region, we add them to the tree. We then add those nodes to the active set. So now we have this complete new set of active nodes that are ready for the next iteration of node extension. So now in Kinopack star, we repeat this cycle of 3 subprocesses for some fixed time duration. And we gradually improve the solution found until the time runs out. So looking at the properties of this algorithm, we have a few interesting properties. One is we have asymptotic near optimality. So as we run this algorithm for n iterations, and as n goes to infinity, we will be within delta cost of the optimal trajectory. Now the proof for this property for Kinopack star is quite involved, and I have backup slides on it if anybody has questions afterwards, but I'll be going over just an intuition of the proof. So imagine we're given an optimal trajectory x star with these nodes along the trajectory that are cost c delta apart. Now, if we overlay the decomposition from Kinopack star over it, we have this set of regions R star that contains a node from the optimal trajectory. So these purple regions. Now, the goal of our proof is to demonstrate that Kinopack star will generate a delta optimal trajectory to any of these purple regions, eventually to the last one, meaning we have a near optimal solution. And you might be wondering, how do we get this delta value? Well, we actually define it as the diagonal of a region. So as this region becomes more fine, we will become closer to the optimal solution. And the size of the decomposition is a tuning parameter of Kinopack's and Kinopack's star. So we first proved that Kinopack's star will extend from a region Ri minus 1 star infinitely often, eventually generating a delta optimal trajectory to the next region. That will look something like this. So this is the case where Kinopack star generates a delta optimal trajectory from one region to the next region. And that can continue for each region where we sequentially go down each of these regions, where eventually we will generate a delta optimal trajectory from region Ri star to Ri plus 1 star. Now, this brings us to the other case of our proof, where this delta optimal trajectory might not actually be accepted by Kinopack star. And if it's not accepted by Kinopack star, that means that there must exist another node within this region that is lower cost than this delta optimal trajectory. And that looks something like this, where we have this lower cost trajectory that actually skips this middle region. But since this blue dotted region is delta optimal, and it has a cost greater than this black trajectory, the black trajectory must also be delta optimal. So those are the two cases for Kinopack star generating a delta optimal trajectory to a region Ri star. Either it sequentially goes from one region to the next, or we skip a region. But in either case, Kinopack star will generate a delta optimal trajectory to any of these purple regions, which means we do have asymptotic near optimality. And since we're able to find this near optimal path, we also have a form of probabilistic completeness called probabilistic delta robust completeness. So this brings us to our experiments where the environments are largely the same, except we've added this corridors one, which is actually very complex, and it's this winding narrow passage, and the trajectory is quite long. For our dynamic models, they're the same as our previous experiments. First, our comparison algorithm, we tested it against SST, which is an asymptotically near optimal algorithm. However, we ran it only on a single core this time instead of doing coarse grain parallelization. And we also tested it against Kinopacks. And for our cost metric, we chose path length. And all algorithms use the same method for state propagation, state validity checking, and cost calculation. And we allowed for a maximum planning time of 5 minutes. So for our first example, we have this version of Kinopack star, which is optimized to quickly find initial solutions. So we call it Kinopack star large delta. And this basically, we tuned it to have a very large or a larger decomposition. So the delta is larger. And we also gave it a small memory allocation on the GPU. And that allows it to iterate through the subprocesses more quickly but we generate less trajectory segments per iteration. And here we're comparing Kinopax in blue to Kinopax star with this large delta in red. And we see that Kinopax star actually finds initial solutions faster than Kinopax does, which was pretty interesting. And we found this to be the case for the simpler systems like the 60 double integrator. So Kinopax star is able to find initial solutions in around 4.7 milliseconds. And if we compare this to SST over the whole 5-minute duration now, SST is this green data. SST's median solution is far off what Kinopax and Kinopax star are able to compute in milliseconds. And you might be wondering why Kinopax has such a good cost. And that's because our cost metric is path length. And since Kinopax is incentivized to explore or expand into unexplored regions, the trajectories that hit these unexplored regions first will be the straightest path trajectories. So the trajectory to get the goal first will be a straighter path trajectory. So our next test is with this other variant of Kinopax star, which is tuned to have a very small delta. So it has a much finer decomposition, and we gave a very large memory allocation on the GPU. So the iterations go slower, but we generate many trajectory segments. And now we're planning on this narrow corridors environment, and we're comparing Kinopax star with the large delta to the small delta. And as expected, the small delta finds a much more optimal solution, but the time to first solution is much slower. So we ran 100 simulations, and all 100 found a solution in around 3 seconds, while Kinopax star with the large delta is less than a second. Now, if we compare this with SST over the full 5-minute planning duration, SST doesn't even really appear to be asymptotically improving or finding some near optimal solution. And that's because this problem is so difficult that it requires many iterations of node selection and node extension. And this 5-minute duration is just not enough for it to approach some near optimal solution. So now Kinopax star with a small delta is far outperforming what we see for SST. So if we take this a step further, so instead of planning for the 60 system, we're on a 12V nonlinear quadcopter system. In all of our 100 simulations, SST never found a solution within 5 minutes. So we removed that data from the plot. And now we're comparing Kinopax in blue, Kinopax star with the large delta in red, and Kinopax star with the small delta in pink. And we can see that Kinopax star with the small delta is improving over this full 5-minute time duration. If we zoom in on this figure, so now we're back in milliseconds here, we see that Kinopax is able to find its initial solutions faster than Kinopax star is for this large delta. So it finds it in around 250 milliseconds, while Kinopax star improves to better than Kinopax at around the 2-second mark. So that's pretty interesting. Now here is a GIF of this narrow corridors problem where you can actually see how hard this problem is, especially if you find a better trajectory to one of these earlier states, you have to recreate, the whole narrow passage part. And if we compare the first solution to the final solution, we see initially the solution is wasting a lot of path length in the Z direction of the workspace. So it's going up through the workspace and back down and up and down. While the final solution, not only is it almost a straight line, but it's continuously increasing in the Z direction. So we also have an experiment that shows the different solution types that Kinopax star can find. So the easiest solution is this very wide path here. And then there's a few different shortcuts like this narrow passage, this shortcut here, and another very narrow passage here. And Kinopax star is able to find all of these solutions. And if we compare the first, intermediate, and final, it looks like this, where you can see that it gradually finds better solution types, which can be extremely hard to find. So that's the summary of the work I've been doing, or this is the summary of work we've been doing. I presented 2 novel GPU accelerated motion planning algorithms. These are the first of their kind GPU accelerated Kino dynamic SBMPs. They present huge improvements over traditional state-of-the-art methods. We've even extended it to provide near optimal solutions. So for future work, the immediate next steps that I want to work on is to further improve Kenopac star. I want to further refine the behavior that's happening in these sub-processes. And for the longer term goals, I believe the next step would be some kind of real world robotic testing. All of the work I've done has been in simulation, not even in gazebo, but I believe some kind of gazebo testing and then real world flight testing would be very interesting. That's it. Thank you.
I have time for a few questions.